Hello everyone, my name is Hadi Farid, and this is a video about how Flim, my filmic color transform, works on a high level. I am not an expert by any means, and most of what I've learned is thanks to Troy Sabatka, the author of AGX and Filmic, Nihal Rahman, a CGI and color science enthusiast that introduced me to the world of color science, and the valuable resources they recommended to me for learning about this stuff. Flim is a color transform that takes in linear RGB color data from an HDR scene and outputs RGB values that are bounded in the 0 to 1 range in a way that's similar to photographic film. Flim is just an approximation and doesn't perfectly model film in a physically accurate way, but it's sufficient for most purposes, like tone mapping in 3D scenes, HDR videos, or video games. Before digital cameras were a thing, film was the primary way to capture visual representations of scenes on physical media. Here's what Wikipedia says about film. Photographic film is a strip or sheet of transparent film base coated on one side with a gelatin emulsion containing microscopically small light-sensitive silver halide crystals. The sizes and other characteristics of the crystals determine the sensitivity, contrast, and resolution of the film. Okay, here's the simplified explanation. Film consists of tiny grains of silver halide. Now, silver halide gets electrically charged when light hits it, but you can't see those charged particles with the naked eye, so with some chemistry, we turn the charged silver halide crystals to actual silver molecules. Then, with some more chemistry, we wash away the unexposed silver halide crystals and we're left with a negative with opaque parts of silver for bright spots and transparent portions for dark spots in the original scene. By shining a bright light source from the back of the negative, we can expose a light-sensitive print film and get a photo that more or less resembles the scene. Now, print film isn't paper, but it's close enough that I'll treat it as paper for the rest of this video to make my explanations simpler. There are a bunch of reasons why you might want to use film emulation in computers. In photography, the values captured by the camera sensor might be too bright to display on a monitor, and simply clipping those will look absolutely horrible, and is unfortunately very common on the internet. The same thing happens in 3D rendering, where some parts of the scene might be too bright to replicate in the display device. Film emulation can help in both of these situations because it approximates how a print film will look. Earlier I said that I'll treat print film as paper. So what do papers and displays have in common? They both have a maximum brightness level. The RGB values in your monitor can't go above 100%, and paper can't reflect more than 100% of the incoming light. Film reaches this limit in a very smooth and natural way, hence why you might prefer it over just clipping the values. Even if we don't have particularly bright spots in our scene, film still provides a pleasant and natural look, commonly known as the film look. To simulate film in computers, we'll need to make a mathematical model of it. We could go really low level and simulate the individual grains of silver halide and photons hitting them, but that would be too computationally expensive for practical use in real-time graphics or video editing, so we'll make a simpler model. Let's start with black and white. Assume there is a tiny square patch of film which we'll call pixel for the rest of this video for simplicity. An image can be treated as a grid of these pixels. Next, we'll associate a number with every pixel that simply represents or is at least proportional to the density of grains that are exposed to light in that pixel. This number will be 0 in the beginning, meaning the pixel is unexposed. If we model how incoming light changes a single pixel's density, we can easily transfer that model to a grid of pixels. But take note that this makes an implicit assumption that nearby pixels have no relationship, which is inaccurate, but it will suffice. Let's go back to a single pixel. When light particles hit the surface of a pixel, its density goes up in a nonlinear fashion. We can approximate this relationship by taking the logarithm of the input energy and passing the result through a sigmoid function. A sigmoid function is a mathematical function whose graph has an S-shaped curve. For our purposes, the sigmoid function we use must be continuous, and its input and output values must fall in the 0 to 1 range. We glossed over one important fact, which is that real film reacts differently based on the incoming light's wavelength, or its spectral power distribution, but we'll assume it shows the same behavior for all wavelengths in our simple model. We'll also ignore physical units like watts or watts per meters squared or whatever. Anyways, let's imagine the incoming light energy is 120 units for our little pixel. If we take the logarithm base 2 of 120, we get something like 6.9. We'll call this the exposure. Before we put this value in a sigmoid function though, we should remap it to the 0 to 1 range because that's what the sigmoid function expects its input to be in. This is where we define the sensitivity range for our pixels, meaning at what light energy does the density start to go up, and where it stops reacting to increasing light energy. For this example, we'll use an arbitrary range of -14 up to 18. This means the pixel's density value only starts going up when our incoming light energy surpasses 2 to the -14, and it stops changing when the input reaches 2 to the power of 18. Let's make a basic function in pseudocode for mapping numbers from a custom range to the 0 to 1 range. First, we'll subtract the start value from x and then divide that by the span of the range, which is just end minus start. For values below start, we should return 0, and for values above end, we'll just return 1. This is called clamping or saturation. Remember that our exposure value, the log 2 of the input energy, was 6.9. If we remap this number from the sensitivity range -14 to 18 to the 0 to 1 range, we'll get 0.65. Let's now put this into a sigmoid function. Now there are plenty of sigmoid functions out there, but SmoothStep is a good candidate, so we'll start from there. If we put 0.65 in this function, we'll get 0.72 out. We're one multiplication away from calculating the final density value. That's because different types of film have different maximum densities. Let's set our fictional pixel's maximum density to 12. 12 times 0.72 is roughly 8.7. So that's it. That's the density of the exposed grains in our pixel. But how do we go from the density to the percentage of exposed grains? We need a function that returns 0 when the density is 0 and slowly gets closer to 1 as the density goes up to infinity. That sounds like an inverted exponential function to me. If we take a number, say 2, to the power of negative density, and we graph this for all density values, we get a curve like this. Now this is inverted because it returns 1 when the density is 0, but that's actually what we want. When we develop a real piece of negative film, the parts that were more exposed to light become dark and opaque, and the parts that were not exposed enough become transparent. So this function is a good approximation of the brightness of the pixel after being developed. And by brightness, I mean how much it passes light through. Later, we'll reuse this formula to get the brightness of the print film. So in that case, brightness means how much the print reflects light. That was a lot to explain in one go. Let's quickly recap how we went from incoming light to the final brightness value of a pixel. We started by taking the log base 2 of the input energy to get what we call the exposure. Then we mapped that exposure from the sensitivity range to the 0 to 1 range before sending it through a sigmoid function. We then took the output from the sigmoid function and multiplied it by the maximum density of our pixel, which we arbitrarily set to 12. Finally, we used a basic 2 to the power of negative density function to get the approximate brightness of the pixel after being developed. Okay, let's combine all of that into a single giant function. We'll start with a good old log base 2. Map that from the sensitivity range to 0 to 1 with clamping. Put all of that in the smooth step and multiply the result by 12 to get the density. And finally, take 2 to the power of negative all of this. We now have an approximation for how a black and white negative will look after being exposed to light and then developed. To burn this onto a print film in real life, we shine a bright white light from the back, which is aptly named the backlight. This light will easily pass through the transparent parts of the negative, which were originally exposed to less light from the scene, and correspond to shadows and dark spots. Opaque parts of the negative, however, will block the backlight. Remember that these opaque parts were exposed to more light, so they correspond to brighter spots in the original image. This essentially inverts the negative, which was inverted itself, so what we get on the print film resembles the original scene. We could simulate the process of printing with a new model, but the one we already made for negatives works perfectly well for this as well. All we have to do is to pass the input energy through that giant function twice. Now, of course, we could and probably should use different parameters for the two passes, like different sensitivity ranges or different sigmoid functions. In Flim, the only thing that changes between the negative and the print pass is the maximum density and the strength of the backlight, which simply scales the output of the negative pass by some amount. The input energy can also be multiplied by some factor. Notice how the notion of density seamlessly transfers to printing, where it represents the density of ink. Also notice that the output never reaches 0. This is because of the nature of exponentials. Later, we'll call this bottom limit the black point. To get a sense of how well this concept will work on real images, we'll use Blender's shader nodes. Blender is a free and open source 3D creation software with tons of features even outside 3D. You don't need any experience with Blender to understand this part. Here I have a linear image, also known as an HDR image, textured onto a plane in Blender. We can calculate a grayscale value by just taking a weighted average of the RGB channels, typically giving more weight to greens and less to blues because of the internals of the human eye. Next, we calculate the log base 2 of the grayscale value and map it from the sensitivity range to the 0 to 1 range. Fortunately, Blender's map range node already supports smooth step, so we don't need to implement it manually. Let's multiply the output of the sigmoid function by the maximum density to get the density value. And finally, take 2 to the power of negative that to get the brightness. Next, we'll put all of these nodes in a node group. We'll make an input parameter for the maximum density. Let's name this node group Film Pass. Observe how the image changes when we play with max density. As expected, if we scale the input by some amount, the negative gets brightened or darkened in the opposite way. Let's also scale the output and then send it through another film pass node and play with the parameters. And just like that, we have a very simple black and white film approximation. Let's compare the final image with the original image, which was clipped. See how the highlights have become smoother and how the image has slightly more contrast, although the contrast can be decreased or increased by changing the parameters. Color is typically represented by 3 numbers or components in computers, each representing the amount of red, green, and blue. The triplet 000 represents black and 111 represents white. 100 is pure red and 0.2.9.1 is a bright green, and so on. So-called linear or high dynamic range images can contain triplets with RGB values above 1 or even below 0, as we'll see later. These numbers have no meaning on their own, so we need to define a color space that we work in. Back in 1931, some smart nerds were trying to quantify color in an accurate way, so after some experiments, they gave us the CIEXYZ color space. It's not actually possible to create an absolute color space because color is partly psychological, and trying to accurately model the human vision is impossible as it's extremely complicated and not yet fully understood. Also, different people see colors differently. However, the CIE model is good enough, and most importantly, it's practical. A color space consists of 3 primaries, a white point, and a transfer function. The primaries define the XYZ values for pure red, green, and blue in the color space. This is also called the gamut. The farther away the primaries are from each other, the wider the gamut becomes, allowing us to represent purer, more laser-like colors without using negative values. The white point defines how cool or warm gray values like 111 will look in the color space. For example, illuminant E or IE stands for equal energy, meaning all wavelengths have the same intensity. Another common white point is ID65 or daylight 6500 Kelvin. The transfer function of a color space defines whether the RGB values are linear or nonlinear. Linear color spaces are used in physical calculations like rendering a photorealistic scene, while nonlinear spaces can be used in color grading, display devices, or cameras. We can convert between different gamuts and white points using 3x3 matrix multiplications, although transfer functions need to be handled separately. Some standard color spaces include sRGB, which is what most display devices use, linear RIC 709 or BT709, also called linear sRGB, DCI P3, display P3, and BT2020, which has a very wide gamut and is used in some laser projectors. By default, Blender uses linear RIC 709 as its working space, and it's what we'll use for our model as well. It's fairly straightforward to extend our Filmic model to support colors. The basic idea is to have 3 layers of color filters, each of which is sensitive to red, green, and blue light respectively. Let's call that the sensitivity tone of a layer. Each layer starts out transparent, and as the incoming light of the sensitivity tone hits that layer, it slowly turns into the opposite color of its sensitivity tone, which we'll call the ink tone. So the red layer, for example, slowly turns from transparent into a cyan filter as it receives red light. The green layer turns magenta as it receives green light, and the blue layer goes yellow as it gets blue light. The 3 layers are then stacked up to get the final color. This stacking up can be modeled by multiplying the 3 layers together component-wise, and note that the transparent state is represented as white in our model, because a white filter leaves the image unchanged. Somewhat confusingly, this is named subtractive color mixing even though it uses multiplication. Once all the layers are multiplied together, we'll get a color negative. We can then shine a backlight and expose a color print film to the negative and develop it to get our final image, just like we did in black and white. We'll use Blender once again to see how this concept works on real images. We'll start by separating the incoming color into its red, green, and blue channels. It should be obvious that we're going to use our giant function again, but this time to get the percentage of mixing from white to the ink tone. So let's recreate our film pass node. We'll make sure the input doesn't have any negative values because logarithms hate them. Negative values in linear images can come from so-called out-of-gamut colors, which are too pure to represent with our current color space, which is Rec 709. Clipping these values to 0 is called gamut clipping. There are different methods for removing these negative values in a smoother way called gamut compression, but we won't use them here. Since logarithms tend to negative infinity when we approach 0, we'll add a tiny offset to the input to avoid numeric issues. It's neither necessary nor accurate, but in Flim, this offset is equal to 2 to the power of sensitivity start. We won't implement that here. Let's finish up the film pass node. Add a color mix node and mix from cyan to white. Use our film pass node on the red channel to get the mix factor. And do the same for the green and blue layers. Then multiply them together. We have now got a nice color negative for ourselves. Let's make this a node group and call it color film pass. Make a parameter for max density. Then duplicate the node for the print pass. Let's scale the input by some factor. In fact, we can get the factor by taking 2 to the power of a custom exposure value. Let's make that a node group and call it exposure. Let's multiply the output of the negative pass by some color. Can you guess what this is for? This is the color of the backlight. We can also adjust the exposure for the backlight. Let's play with the parameters and try to roughly match the input and the output images. In the color film pass node, we can get artistic color adjustments by using different sensitivity ranges for each layer. Let's put all of this in a single node group named color film. If we replace the input with pure black, the output will not be black, but something slightly brighter. We observed this effect back when making the giant function and called this the black point. This isn't necessarily a problem, and it's similar to how real prints work, but if you really want to get rid of it, you can simply input pure black into a separate color film node and subtract the result from the output of the main node. To avoid color shifts, you can make this a monochromatic operation by observing what happens to the average of the RGB values after subtraction and applying the same factor on the output. Make sure to avoid division by 0 though. Unfortunately, our current model has a huge flaw. To demonstrate it, let's replace the input image with an RGB color sweep. Instead of slowly turning to white, the colors get stuck. This ugly effect is caused by the fact that the 3 layers are completely unaware of each other. If only there was a way to introduce crosstalk between the 3 channels. Here's an idea. What if we make up a new gamut whose red channel is affected by all 3 channels in our current gamut, which is Rec 709? For example, the red channel's value in this made-up gamut would be equal to 90% of the red channel in Rec 709 plus 5% of the green channel plus 5% of the blue channel. And each green channel would be equal to 90% of Rec 709's green channel plus 5% of each of the other channels, and the same goes for the blue channel. We can implement this with dot products. Let's combine the results of the dot products to create a new RGB triplet which belongs to our new made-up gamut. This is actually just a matrix multiplication in disguise. We're basically multiplying a 3x3 matrix by a 3D vector, which is our input RGB triplet. the rows of the matrix are simply the factors we use to define how the channels get affected by each other. Let's abstract away these dot products into a new node named matrix multiplication. Let's also make a node group that simply outputs the rows of our matrix. This transformation effectively desaturates the input image before feeding it to our color film node, so we need to undesaturate it by reversing the transformation after film emulation. This can be done by multiplying the inverse of our matrix by the output color. We're not going to get too in-depth, so we'll just use this formula from a user on Stack Overflow. I know this is one miss of a node graph, but this is the nature of matrices. If you're using a programming language, this could be as simple as a function call. Let's hide this in a node group and name it matrix inverse. Finally, let's multiply this inverted matrix by the output of the color film node. We can see that it has removed the desaturation from the image. However, this transformation has unfortunately introduced some ugly clipping into our image. Here's an exaggerated version to make it more obvious. Now this clipping is expected because we're doing our film emulation in a wider gamut and then converting back down to Rec 709, so we'll inevitably get out of gamut colors here and there. To mitigate this, we can modify our Sigmoid function or gamut compress the output. You can check out this super simple gamut compression algorithm published by Jed Smith on GitHub and implement it if you want to. We won't do that here though. Right now, our gamut conversion matrix is pretty unintuitive to tweak. It's just 9 numbers that do random things to the image. So let's go back into the gamut matrix node and add some parameters like scale and rotation for each channel. We'll use the hue saturation value node to essentially desaturate each channel as its scale goes up and shift its hue based on the rotation. This method is kind of arbitrary and not necessarily accurate, but is convenient. We'll make sure to divide the final triplet by the sum of its components so that they add up to 1. Let's set the scale to 1 for start. Now the image looks broken, but that's because the first matrix multiplication still uses the old parameters, so let's set its scale to 1 as well. It would be nice if we could modify both of these nodes at the same time, so let's put this in a node group and use it instead. I'm playing with the parameters to see what effect they have on the image. Let's replace the input with a real image and try to make it look good. Let's try another image that has a lot of deep blue. If we disable and enable the matrix multiplication nodes, we can observe how it's useful to do our film emulation in a wider gamut than our working space. It should be noted that black point compensation must be done in the working gamut and not in the wider gamut, so let's quickly fix that. Let's try a few more images and see what film emulation is doing to them. Hopefully, by now you have some idea of how we can mathematically approximate film in computers. It's important to note our model lacks many features of film, including the pleasant noisy look of film grain or halation in color film, which causes a red glow around bright objects, and many more effects that naturally happen in real film. Our model is only concerned with mapping a linear RGB color to the 0 to 1 range in a way that roughly resembles film. Keep in mind that our model has some differences with flim, but it's close enough. This video was made by one person for free, purely out of interest in this topic, and is completely free to watch. So if you've been enjoying it, consider giving it a thumbs up and subscribing to my channel. And leave a comment if you have any questions or observations. Thanks for watching.